Well, hello and welcome. In this video, I'll be covering section 2.7, which is over implicit differentiation. My goal for you by the end of the video is to be able to find derivatives both explicitly and implicitly. So let's go ahead and start by talking about those two key words I just said there, implicit and explicit. So with most of the things that you have dealt with thus far, you've had it in what we would call the explicit form. That basically means that one of the two variables is actually being defined or is written in terms of the other. So as you can see with the examples here in the middle, something like y equals 2x plus 3, a linear equation, that's an explicit form of that particular equation. So notice all of them, if you look at each of the other two, actually all three combined really, notice that there's a single variable that's isolated, and then everything else is the same variable on the opposite side. So it's again, each one is being defined in terms of another. Whether there's one term, two terms, doesn't really matter. It's just one is isolated, the other side contains as many of the other variables as needed. However, there are some others that have been presented to you guys in implicit form. For example, like an equation of a circle. The first example here, x squared plus y squared equaling 16, where notice neither variable has been defined in terms of the other. They're actually both kind of intermingling on the same side of an equal sign. Another example would be like the rational function, the xy equaling 1, which really is a hyperbola, where you could say that you have that one where you could isolate y, but it's in its current format, x and y are on the same side, so neither is, again, defined or put in terms of the other. And then the last one there is just a linear equation, 2x plus 3y equaling 6 in standard form, where again, notice your x's and y's are actually on the same side. Neither of them is actually isolated. So if you think in terms of what our class is currently exploring, this concept of differentiation, we're now going to, in this video, kind of explore the concept of how do I deal with those that are in implicit form, and how do I actually find, say, derivatives of those so I could find equations for slopes. So what's nice is when something's provided to you in explicit form, everything that you've learned so far, as far as the rules, such as product rule, quotient rule, chain rule, everything just gets applied as normal as you've learned it, because it's going to be with respect to one of the variables, usually in terms of whatever you would consider the independent variable. Now, however, when an equation is in implicit form, you have to actually consider what variable you're differentiating with respect to a little bit more carefully. Technically, we always need to know what variable we're doing with respect to, but for this one, it's even that much more important. And then we have to assume that the other variable is actually defined implicitly by whatever variable you're doing with respect to. So for example, if you have an equation with x's and y's and you're differentiating with respect to x, which is pretty normal for what we have been doing, we actually would assume that the variable y is defined as a function of x. So by doing that, that would then allow us to apply the chain rule as we've learned it whenever you have to take a derivative of a term that actually contains that variable y. So on occasion, you can actually deal with these implicit either equations or functions by actually turning it into an explicit form, and then that allows you to then differentiate as you guys are comfortable with. So one example of this is as seen here, where I just need to find dy over dx, so the derivative of y with respect to x, for this equation, x squared times y equaling 1. This particular one is one where we could get the y by itself relatively quick by just dividing by x squared, which then would give us the equation y equaling 1 over x squared, which again we could rewrite that in terms of negative exponents and call that x to the negative 2 power. And now we should be able to find the derivative with respect to x. So dy over dx is being equal to, and now just power rule with that x to the negative 2 power, so negative 2 would come out front, and then the power would drop by 1. And now I can go ahead and move my negative exponent to the denominator and say that the dy over dx actually is equal to negative 2 over x to the positive 3 power. So notice, even though it was presented in the implicit form, we still had a strategy that allowed us to find the derivative. But again, not every single equation is going to be as easy as this to be able to actually turn into an explicit form. So before we get going too much further, let's go ahead and just explore a little bit of how do I differentiate terms just with respect to x, even if the letter doesn't match. So as it says at the top here, and I just mentioned in the previous slide, not every equation is super easy to turn from implicit to explicit. So what we end up doing is this process that we actually have a name for called implicit differentiation. Not very creatively named, obviously. So what we need to kind of understand here is that if we have the derivative of y with respect to x, the notation for that is this dy over dx. So basically, if I need to take a derivative of y with respect to x, we know that dy over dx is our notation that we're going to get to use. So each of these, notice it just says to differentiate with respect to x, so each one, well, the first two have two terms, the last one's just a single term, and it's actually a product, so I'll have to use product rule on that one. But if I took the derivative of this first one, letter a, the derivative of x with respect to x would just be 1. The derivative of y we just mentioned is actually just dy over dx. Now if we were to look at this middle one, again, notice that when it's only an x, everything is normal. We don't have to change our thought process at all. So this next one, the derivative of 2x, that's just going to be 2 plus, and even though this has a coefficient, remember coefficients can just kind of hang out there, the derivative of y would just turn into, once again, dy over dx. Now this last one's going to be a little bit tricky, and this is where you're actually going to see why we brought up the idea of we would be able to utilize this idea called chain rule. Is even though this is a product, I'm going to have to use product rule. So again, if I did, let's go with the derivative of the first, which would just be 1 times the original second, so 1 times y squared. Nothing really seemed too crazy quite yet, hopefully. Then I'm going to add that with keep the first times the derivative of the second. So this is where things will get a little bit different. We have to treat that y like it's a function. So again, that's like there's a function inside of a square function. So I would deal with the square, because that's the outer function, so that would turn into 2 times y, and the power drops by 1, so it'll just be y to the first. But then I have to do times the derivative of that inside function, which we're saying is y. Well, we just, as we saw with the last two examples, hopefully, we saw that the derivative of y with respect to x just turns into dy over dx. So if I kind of simplify or clean this up a little bit and get rid of some of the multiplication I don't really need, like 1 times y squared, that really would just be y squared, plus, and then having x times 2 times y, that's kind of a silly way to write that. Probably reorder it and just say that's really 2 times x times y, but then it's also still times dy over dx. And that would be essentially each of these expressions. Notice there's no equal signs with these, it's just how do I actually differentiate just specific terms in terms of or with respect to x. Hopefully seeing these three examples gets you a little bit more familiar with, okay, this is how we're going to deal with the y. But as we go through the video, we'll explore it even more in depth. So just like anything else that we encounter that's going to be a little bit more complex, it's kind of nice to be able to somewhat break it down into what's my step-by-step process. So this idea of implicit differentiation is going to work, at least with these steps. We're just going to have the assumption that we're going to have an equation that has x's and y's, and y is considered a differentiable function of x. So if I needed to find the dy over dx, in other words, just the derivative of that, either, I guess in this case it would be an equation, so there would be an equal sign here. We actually just differentiate both sides of the equation with respect to x. So instead of only worrying about a single side like we have been for the most part thus far, we actually are going to treat this, since each equation has two sides, we're going to kind of treat each side like its own little problem. So differentiate each side with respect to x. Remember, every time you have a letter that's not x, such as y, you'd have to multiply using chain rule. So at some point in time, a dy over dx would have to get involved. So what we end up doing after we get that differentiation of both sides accounted for, we then write the results so that all of our dy over dx terms are on one side and everything else is on the other. So you can kind of think of that in terms of, if you wanted to make this a very specific plan, you could just say, I'm always going to move the dy over dx terms to the left, and everything else that's not dy over dx or doesn't have that attached to it, I'll move to the right. That way you can maybe make it a little bit more consistent for yourself. But again, it does not have to go to the left side. You can put it on whichever side is easiest, at least according to what your gut instinct is, and just realize that every other term without a dy over dx has to go the opposite direction. What that allows us to do by collecting all of those dy over dx terms is that then should allow us, if they're all on the same side and have a dy over dx, I should be able to factor that dy over dx out. And so now if I had, say, 2 or 3 dy over dx's, when you factor it out, it should just turn into a single dy over dx outside of a set of parentheses. So what we then do is try and just isolate that single dy over dx by just dividing everything by that resulting factor, so whatever that parentheses turned into, and whatever that result is, if I can simplify it, I go ahead and do it, but that should then have our dy over dx isolated, which then means we've technically solved for what the derivative of that implicit equation was. So again, we'll explore that a little bit more in depth with the next few examples. We've got 3 of them to go, so hopefully these will start coming together and make sense. And we'll go ahead and ease into this process with something that's a little bit more familiar to us. So hopefully you recognize that this is an equation of a circle, as you can see from the graph, but x squared plus y squared equaling 25. Just hopefully a quick little analysis of that. We know that the center for that circle would be 0, 0, or the origin, and then the radius would just be the square root of 25, so a radius of 5. So hopefully that graph does not surprise you, that that's what that expression really looks like, or that equation looks like. What this wants us to do is find the slope of a tangent line to the circle at a specific point, 3, negative 4. So if we go ahead and just kind of get a little visual for where is that point, if I go over to the right 3 and then down 4, it's really saying let's find the equation of the line that would be tangent to that circle right there. So how do I come up with the derivative? Well, even though this is implicit, we still will just take the derivative of both sides. And so if I look at the first side, just treat it like that expression, x squared plus y squared, just like we did on 2 slides earlier. The derivative of x squared should just turn into 2x, and then the power drops by 1, so power of 1, so I can just say it's 2x. The next one is going to be, let's treat this like it's a function inside of another function, so we'll do the power part first, so 2 comes out front, y times and then the power drops by 1, but then it's going to be times the derivative of that y function, which every time is going to be dy over dx. Just by definition, that is the derivative of y with respect to x. On the other side of the equation, that's just a constant, so the derivative of that constant should just turn into 0. So now I need to collect all of my dy over dx terms on one side and move everything else to the other. Well, there's only one dy over dx term. It's that 2y times dy over dx, so I really only have to move the 2x over. That then gives me an expression 2y dy over dx being equal to a negative 2x. So with this one, I really don't have multiple terms to try and factor out. That's already kind of its own factored form. So all I'd have to do is just now solve for dy over dx. So divide both sides by 2y. And that then would give me this expression of dy over dx for this equation is equal to negative 2x over 2y. So the 2 should be able to cancel. So really it's just negative x over y. So now how do I find the slope at the point that they gave us? So at 3, negative 4, the point that they want, I essentially just plug in this scenario, actually both variables into that expression to come up with the slope. So my slope will be this negative x over y, so negative 3 over the y value, negative 4. So it looks like it would have a slope of 3/4. So if I wanted to now come up with the equation of that line, I could, but we also could just go back and instead of having this rough sketch, I can actually be a little bit more, I guess, specific about the slope. I can go from that point that we plotted, 3, negative 4, do a rise over run of up 3, right 4, and I can also go down 3 and left 4, And that gives me now 3 points that I can be a little bit more accurate with how I would actually draw that specific tangent line. Let's move on to another example where this time all I have to do is just find the derivative. I don't have to actually plug anything into it, but as you can see, this function, pretty interesting looking graph. But what we would do is go ahead and just follow through with the steps. I just take the derivative of each side. So if I did that individually, notice you have y cubed. If we kind of see the pattern that we had before, the 3 would come out front. Y would now have a power of 2 on it. But it's going to be times the derivative of the y. So that's where dy over dx once again gets involved. Then I'll do the same thing with the next term. So I've got y squared, so that should turn into 2y. And then times the derivative of y with respect to x, so dy over dx. Notice again, it's kind of a chain rule situation. We're dealing with the power part first, leaving y alone, but then multiplying by the derivative of the y with respect to x. So notice each one of those has gotten that dy over dx. The next one, I have -5 times, well, this one's not as much of a chain rule. It's just going to be what is the derivative of y with respect to x. That's still, again, dy over dx. Now I finally get a term that doesn't have a y on it, so I'm just differentiating this negative x squared, which would just turn into a -2x. And then the power again would be 1. And then now I can go to the other side of the equal sign, take its derivative. Once again, it's a constant though, so I can just say that is going to equal 0. So now I have to collect all of my dy over dx terms on one of the sides. They're already kind of all on the left side, so it really is going to be simple to try and get them as the only terms that have those on one side just by moving that 2x term over. Now that gives me the ability to, if that term was gone, notice each term has dy over dx. So you can kind of do a combo step and just say, well, I'm going to factor that out since they all have it in common and just see what's left. Well, that would leave 3y squared plus 2y minus 5 in parentheses. And then the other side, we've already moved that 2x over, so it's just equals 2x. So to get dy over dx by itself now, I just divide by the parentheses, so 3y squared plus 2y minus 5. And as long as I do it on both sides, everything's fine. It balances out. Notice now I have my derivative equation, dy over dx, all by its lonesome, being equal to that expression, 2x over the 3y squared plus 2y minus 5. So if I now needed to find the slope at specific points, I could, or even if I wanted to do, where is this going to have a like horizontal tangent line, you can kind of see on the graph that probably is going to be at the very bottom at an x value of 0, but the reason I could guarantee that I know that is to set this equal to 0, which that means the top is the only thing that I had to worry about. And where does 2x equal 0? Well, that would be at 0 itself, hence why that would be a minimum here on the graph, as you can see, for a tangent line with a slope of 0. If I needed to find where it was maybe vertical or undefined, that would probably be at like this point right here and this point right here. That's more than likely going to be whenever the denominator equals 0. And I could solve for that y value just by potentially either factoring or quadratic formula, or maybe completing the square if we thought that was the easiest way to do it. I'd probably use quadratic formula to set the bottom equal to 0. But I'd actually probably try factoring it first just to see if maybe those numbers work out to be kind of nice. So anyway, hopefully you get kind of the moral of the story here is we just take the derivative of each term individually. Anytime you take the derivative of y with respect to x, you have to kind of attach these dy over dx's at the end. So good rule of thumb is if the letter doesn't match what you're doing the derivative with respect to, you have to put d of that letter over dx attached to, because of chain rule, each of those terms. So had this had a z, for example, if I took the derivative of that term with z, I'd end up having dz over dx that kind of gets slapped on at the end, or multiplied to the end of whatever that term is when you take its derivative. I'll do one more example here. This one's going to be a little bit more of the application side, so I'm actually finding a specific slope as opposed to just coming up with a slope equation. Notice this one, you might recognize the formatting from pre-calculus. This is what we would call a hyperbola, if you remember the shapes of those graphs as well. So this is just wanting us to find the slope specifically at this point, 5, 1. So once again, I'll just follow through with the steps. Derivative of the left side would turn into 2x, then minus the derivative of the 9y squared. Well, 2 would multiply with 9 to turn into 18y, power of 1, but then times, because that's not the letter x, I need to multiply by the derivative of y with respect to x, so dy over dx. And then equals, and I have the derivative of a constant again on this side, so I get to say that that's equal to 0. So similar to what we had with the circle example from not too long ago. Now I'll go ahead and try and isolate my dy over dx terms, or just collect them on one side. Since it's on the left, may as well just keep it on that side. I could have added it to the right and maintained everything be positive, but just writing 2x was more simple in my head, so I go ahead and continue with this route. I've got negative 18y dy over dx being equivalent to a negative 2x. So now if I wanted to isolate the dy over dx, I would just have to divide by negative 18y. The double negatives turns this right back into a positive, like it could have been if we would have moved the 18y dy over dx to the right. So it really didn't change a whole lot of our process. We've got dy over dx now by itself being equal to, and if I reduce this, looks like 2 would go into both numbers. I'd end up with a positive x now over a positive 9y. And so now I should be able to plug in the point that they gave us. So the slope at 5, 1 is going to be equivalent to, if I plug in 5 everywhere I see x and 1 everywhere I see y, that would just turn into a 5 over a 9 times a 1, which really is going to just be 5/9. So if we went over to our graph, we would then be able to kind of see at that point 5, 1, that tangent line does seem reasonable to come back as a positive number, but I could then go ahead and let's see if I have enough here to do a rise over run of 5/9. So I've got 1, 2, 3, 4, 5 down, and 9 over. Looks like it would be right about there if I counted that right. Nope, off by 1. So it would be this point right here. That then, if I were to connect with that line over there, notice it does look like it just glances off. Be a little bit more accurate if I had a straight edge to use, but as you can see here, we're able to find slopes at specific points even when the functions are a little bit more, I guess, complex is a good way of saying it. But this was, like I said, the last example. Hopefully this has given you enough that you can start working through the problems in the homework without issue. But as always, if you have any questions, just reach out, let me know so I can offer my help. Appreciate you guys taking the time to watch the video again, and we'll catch you next time.